Okay, so as we saw, the bigram model was the right model in the sense that it was doing the job that we wanted. The issue was that it was unable to really mimicking the language model because it has no memory. And then the question is how we can just make a memory in this model, or how we can somehow add this whole context inside the text. Well, we should figure out some way that we can somehow inject a longer text, a longer sequence of tokens inside our model. So what is the idea here? Maybe we can start with the bigram model that we had, but then we just figure out some modification to it so that we inject more context. The basic modification that I can do is that I can say, okay, instead of just take a look at the last word, last token, I'm going to look at maybe t different tokens behind, right? And then I'm going to add all of the embeddings together, and then I give it to the bigram model. Okay? So what do I mean here? I mean that if I want to just predict xt plus 1, then I'm going to add all the embeddings for x1 to xt, and then I'm going to inject that adding into my neural network. Okay, so you can think of it like this. So say you want to just find out the next word, then you are not going to simply take the last embedding. You are going to say, okay, x1 plus x2 plus so on. You add up all of them till you get here, and then you're going to give it to your context. So this CT that I'm showing here is now my context of the whole sentence. So it's simply the addition of all the embeddings inside my sentence, inside my input text, and then I give this guy to my softmax unit to predict the next token. Okay? Now, this is a more realistic model because here what we are doing, we are essentially including everything behind into the context, right? We're not looking just on the last word itself. Now, if you want to think about it in an algorithmic point of view, so this is basically that you start from the beginning of the sequence, beginning of the text, and then you add up all the context, all the embeddings together. So you're going to add up all the embeddings till you're over with the sequence. Then you're going to pass that context through the softmax to compute the probability. And then if you want to generate the next token, you simply sample from that output, right? So that output is giving you the probability of the next token, given this context-aware model, and then you're going to sample from that distribution. Everybody's clear what I'm doing? So this is basically bigram model, nothing changed. The only difference is that I have added up all the embeddings before, right? So this model, as I told you, statistically is more realistic. And you might say, why this is more realistic? Well, if you think about it statistically, embedding of every single token in your sequence is somehow representing your token, the word that was inside the sentence, right? Now, when you add it up with the other guys, it's true that it's not the token itself anymore, but it's somehow carrying some of the information, right? So it might have some of the useful information of the token injected into your neural network. So the idea here is that in this form, you essentially have one context, CT, and this CT is proportional to all the tokens you had before. I do know the way that I did it right now here is super dummy, but it's still depending on all of them, right? So if I drop one of the words, if I drop one of the tokens, this context is going to change, right? This means that that context depends on that word as well, right? And now the output of your model is being computed in terms of that context, since your context is depending on everything. So this is a better approximation as compared to only injecting the last embedding. Okay? Now, you might still tell me, okay, this doesn't make still sense. I mean, why it should be more realistic? You are simply adding up everything together. Well, just forget about adding up. Assume that I'm computing a general function. If CT maintains all the information that exists inside x1 to xt, if it can maintain if it could contain all the information available in x1, x2 till xt, if it could do that, then it's gonna carry all the information to the neural network, and the neural network, if trained well, is capable of predicting the next word properly. Okay? So this is again a bit of a statistical flavor to the idea, but I'm just, as I said last time, I'm trying to bring it up time to time so that you get used to it. Okay? So from computational point of view, to you, everything that I'm doing is just simply adding up embeddings, right? But from a statistical point of view, I am just carrying information through time by this adding. Everybody's clear? Okay, great. So now, if I want to do the training for this model, essentially, I am doing the same thing as before. So it's going to look like the bigram model again. The only thing that is going to change is that this time I am not going to take a sequence of length 2, because I don't need one token and the label. I am going to take one longer sequence of length t, with one next token as the label, right? So this is why you see here x1 to t plus 1. So t plus 1 different tokens, consequent tokens. I'm going to sample them. I do b times, and then I'm going to have a batch. Now that I have the batch, now I start to do the training. And if I want to do the training, there is a bit of trick here. I don't need to look at one complete sequence as one sample. Potentially that sequence is multiple samples, right? Because what I can say, okay, maybe I give this one, like you have a sequence of length t, right? So in this sequence of length t, you know that the second token is the one after the first one, right? So you're going to look at this subsequence as another sample, right? You would say, okay, if I give the first token, I need to get the second token, right? If I give the first token and second token, then I need to get the third token, right? If I give the first, second, third one, I need to get the fourth one, and so on until you end with your sequence, right? So this is why I can again loop here over time. So I'm going to say I'm going to give the first token, and then I compute the probability of the second token. Then I go ahead, compute the logarithm of the probability at the label point, right? And then I go for the next one, right? So I'm going to say, okay, this time I'm going to give 1 and 2. Then I see what is the third token, right? I compute the probability. I compute the gradient of the loss. And I keep on going till I'm over with my whole sequence. Now that I'm over, I'm finished with one sample inside my batch. I again go for the next one. I repeat the same thing. Clear what I'm doing here? So now you're looping over the batch and over the time, right? And then you have more samples, more sample gradients. It's going to help you train more efficiently. Okay? So once you have done it, then at the end of the time, again, you are going to do some averaging. Of course, here you have more samples, right? Because for every single sequence inside your batch, you had t different samples, right? And you are going to simply average over time and batch, both of them, to end up having one gradient. Then you update. Yeah? And you keep on doing this for multiple epochs till your model is going to converge. Everybody's cool? Questions? Yeah?
I didn't understand. Are all the samples have the same context length?
No, they don't have.
Oh.
The first one has just context 1.
Okay.
The second one has the context input is addition of anything before, right?
Yeah.
And dimensionally, it's the same thing, right?
Isn't the size, the absolute number is going to change?
Absolute number of people who are tokens who are contributing to your decision is changing. And of course, you want this to happen to your model as well, because you don't want your model to only talk when you give it 10 tokens, right? It should talk when you give it 1 token, 5 tokens, 10 tokens, 20 tokens, right?
So you can train the model with the loss computed from all of them.
All of them, exactly, exactly. This is the trick. I mean, if you drop that, nothing going to happen, right? So you still can train it, but you are not using efficiently the samples that you have. But of course, you can do that as well. Yeah. Questions? No question? Great. Okay. So now, if you do this, you're going to start seeing a bit of more meaningful generation of text. This is not that huge, but still it's going to do something. Because intuitively, you are carrying information, as I said. You're not generating your next token simply based on the last token. You're generating it based on all the tokens you had before. Okay? So this is going to happen, but this is not a very sophisticated model, the one that I did here. And the reason is not simply because it's addition. The reason is because, I mean, you can simply see that there is no sequential order here. And what do I mean by sequential order? So what do I mean by sequential order here? I mean that, okay, if a context of one complete sequence has a sequential order, if I do any permutation in this sequence, then I am going to have different context. How is it? Say I have these two sentences. One of them is Alice drank water. The other one is water drank Alice. They are the same sequence of tokens, right? In the sense that same tokens are happening, but they are permuted, right? So the first one, Alice shows up first, then drank, then water. The other one, water shows up first, then drank, then Alice, right? So two sequences, same tokens happening with different permutation. But the first one makes sense, the second one doesn't make sense, right? Now, in this model that we have here, in this context model that we are doing, so the context that we are building is simply addition of the embedding of Alice, drank, and water. And it doesn't matter if I just put the water first or last. This addition is going to be the same, right? Meaning that the context you get for the sentence Alice drank water and water drank Alice is the same. So your model is going to decide based on the same context for both of these sentences, right? So you cannot expect that model to distinguish between these two sentences, right? Correct? So this guy is lacking the sequential order, and sequential order for text generation is quite important because you want your model to somehow understand which word is showing up where in the sentence, right? And right now, this model that we have made is not doing it. Okay? So without considering the fact that this model is too simple, it has not too many parameters and things like this, we can eventually say that from the statistical point of view, we can simply say that this is not going to do the job because the context itself is not sequentially ordered, right? So it's not following the sequential order of the text. So now how we can do a more sophisticated way of modeling the context or extracting the context from a sequence? Well, we can go ahead with more advanced ideas in sequence processing, and the most, say, advanced working idea before transformers was the recurrent neural networks. So in the recurrent neural network, you have a neural network which not only depends on the input, but also depends on the state. And the state is always computed from the last state of the network itself, right? So each time you use the network, it's going to compute some state as well, and that state is going to be fed back to the network next time, right? So this was the idea of recurrent neural network, and we can build on, based on this one language model, right? So for instance, we can assume that we have one neural network. This neural network can take as the input one embedding xt and one previous context ct minus 1. So ct minus 1 is the context that I have made from point 1 to time t minus 1. And now I want to go for the next word at time t. So I'm going to take this old context. I get my new token xt. Both of them go inside the neural network. And at the output of this neural network, I get a new context ct. So this is the context up to point t. And the distribution of the next word pt plus 1. So my neural network is saying what is the chance of the next word, given that your last token is xt, and from the rest of the sentence, you have the context CT minus 1. And then not only it computes the probabilities, it also gives you a new context, right? So it's going to say, OK, now you have this context CT, which is somehow capturing everything from x1 to xt. Everybody's clear? So this is the idea of recurrent language models. And recurrent language models are the first kind of serious language model which were able to generate text. So in these models, the context CT in every single time is computed from the input at that particular time and the context that you had from the rest of the sentence. And this is theoretically possible to make this context depending on all the sentence before, right? All the text before as the input. And this idea is also capable of capturing the sequential order, because if I have a complicated neural network, then I can make it in a way that when I change the order of the input, the context generation is going to, context computation is going to change. Now, if you want to have a bit of visualization here, you can again think of one neural network here. So this is one general neural network. It has a bunch of parameters W. And this guy can take two inputs. One of them is your current token. The other one is the context, the previous context, right? And then when these two guys go inside, you're going to get a new context and the probability of the next token. So let's start with this sequence. You see the sequence at the top, x1, x2 till xt. And what we want to find out what is the next token, xt plus 1. So the first thing that we're going to do with this model is that we're going to inject x1 into this model, right? So I'm going to put x1 as the input to this model. And as the context, I don't have any context, right? I am at the beginning of my text. There is no context here. So no context with x1 goes in. And I'm going to find out what is the chance of the second token. And what is the context capturing everything from beginning to x1, right? That is C1. Now, I'm going to take that C1, put it back as the input for the next time. Meaning that next time, I'm going to insert x2 as the input. And as the context, I'm using C1, the one which I got last time from the output of my neural network, right? So this is going to be context up to time 1, token at time 2. And then both of them together compute the chance of the third token and the context up to point 2, right? And you keep on doing like this till you get to time t. So at the particular time t, you're going to have xt as the input, the context ct minus 1, which is computed up to the point t minus 1 in your sequence. And then at the output, you could get your context at time t, and of course, the probability of the next token, t plus 1, right? So this guy is now capable of capturing all of those, information inside your sequence if you could train it properly, right? This is a very big if, but if you could do that, then theoretically it's capable of doing that, right? So it's not as dummy as the other guys we had before, which were not capable of doing it. Everybody's clear? Yeah. Sorry?
What's inside the CT here? Is it just a bunch of embedding?
Bunch of numbers, yes. And it has no meaning probably to you, but to the neural network, it just carries information.
I see. So once CT minus 1 get passed into the model, and we get CT here.
Yes.
So what's the difference between CT and C minus? It just includes more information?
Yes. It differs from CT minus 1, meaning that it's somehow telling your neural network that the sentence has progressed at point t like this, right? Yeah. But as I said, these are just, from computational point of view, they are just numbers. And they have no meaning to us, but neural network is somehow understanding that. No. Questions? No question. So how does that pt plus 1 look like? It's a vector of probabilities, right? So it's going to look like this, right? I know why I'm so obsessed by repeating something thousands of times, but you never get rid of me. So it looks like this. You have lots of tokens. Each of them have index, and each of them has probability. Like right now here it says with high probability the next token is a comma, right? But at the end of the day, you're going to sample from that. Half of the times comma comes out. 10% of the time the comes out, right? Yep. N-gram model. No, it's not. I mean, N-gram model in the basic form, that is like there's no neural network. There is a statistical model, right? But then when you want to realize it, this is essentially somehow N-gram. I mean, if you assume that you are processing up to N samples, then this is essentially N-gram. But at the beginning, people were starting to just look at everything like feed forward. And of course, when you want to just do it with one shot, then you are limited in the number of inputs you can get, right? So you could not capture a very long memory. But when you do this, then that N could really be large, right? Yeah. This is the point. Like in the naive trigram is like you take the last two embeddings and feed them to the model, right? Now if you want to have say 10 gram, then you need to have 9 embeddings and fed into this. And this could be very large, right? Like your neural network gonna explode quite fast, right? Preserved, definitely, yes, that is definitely. That is, theoretically that is more stronger than this one, because this is somehow assuming some form of temporal correlation in the sequence, whereas that one is not looking at that. It's just looking at the whole bunch of data and then infer the next one, right? But that is, you are not computationally capable of doing it for a very long memory. Yeah. Yeah. Questions?
For this model, you have to specify the training model
Yeah.
and also the memory model.
Yeah, I'm going to show you the training loop. But yes, in practice, you're going to fix T. If you play around with RNNs, you know that you cannot really make it, again, infinitely large, because at some point they start to forget somehow, right? Because, it's true that they are carrying information, but gradient is going to vanish at some point in time, so you cannot do it for a very, very long time. But compared to one-shot approach, this can have longer. Yeah? Questions? No question? Now, anyone has idea what kind of model I can put here instead of this F? Famous model? GRU you can do. Anything else? LSTM, right? So yeah, we can put GRU or LSTM here. Anything else you can do, but they usually do not converge in training, right? Because of gradient vanishing or explosion. So typical thing that we do in practice is LSTM. You don't really need to know what is inside this module right now. But if you are interested, you can check the recap videos that I put on the webpage. So what is happening here is that you have your cell state, and you have the hidden state of the network at one particular time, t-1. Then you have your input, and LSTM, what it does, it takes the input, it takes the previous states, and then it's going to compute the new state, right? And for you, here, these states are the context. So this is the context that we have. And that xt is the input, the current token, right? So the current token goes as the input to your LSTM. The states of your LSTM is capturing the context. And you keep on going like this in time. Whenever you want to sample or compute the distribution of the next token, you can take the hidden state and pass it through one feed-forward neural network, one MLP, right? Or anything. And then at the output of this MLP, you just get one I-dimensional output out of a softmax, and that is going to be a probability. Everybody's clear? Questions? No question? So now, if you want to think about how we can train this model, essentially we are going to do the same thing as before, but this time instead of just adding up the context, we are going to just do it recursively over time, right? So you're going to start by making one batch of samples, and then once you go over every single sample, you're going to loop over time, right? So you start with some initiate cell state. So the cell state, that is state C, is going to be some dummy value, some empty value, meaning that there is no context right now to your model, right? And then you start from time t equal by 1. So every single time you're going to embed your token. So you're going to get the embedded token. Then you pass the embedded token with the state of the LSTM unit through the LSTM. Then this guy is going to give you the new state. So this is, of course, I'm using it with the same character, but this is the updated version. And this is the probability of the next token, right? And since you have the probability of the next token, and in your data set you know what is the next token, you are able to compute a gradient, right? So you're going to compute a gradient of the loss, the likelihood, the log likelihood, and then you're going to keep it for later, right? And then you go on till you're finished with time and batch, and then finally you're going to average everything out and update your LSTM parameters. If you have embedding included as well, then your embedding is also being a parameter that you are going to update. Questions? Everybody's clear? So you got the idea how you can build one recurrent language model? So efficient forms of this language model are the first generation of the practical language models generating text. So before 2017, people were generating text by this approach. And of course, you have not heard of them you have not heard very good of them at that point of time, but they were working, right? So maybe you were not impressed by them, but some older people were impressed, right? Those who spent lots of time training those models, they were like, oh, finally it's working. Because LSTM was finally working because of gating, right? Anything else was not working before that. So this is the first generation, and this is going to work fine. This kind of modeling has a bit of issue. And that bit of issue is that it's a bit slow. It's going to have a very long delay in the processing. Why? Because if you want to find out what is the context of the first token, you need to pass it, right? But now if you want to know what is the context up to the second point of time, you need to wait till you have C1, then you pass again C1 through your model to get C2, right? Now if you keep on going, each time you need to just, if you want to know what is the context up to point T, you need to wait till this process has been done, right? So the first guy goes in, the context comes out, then again the context goes in, the second context comes out, and you keep on doing till you get in time, right? So this is why people say that recurrent language models can process one token at a time, right? Every single time that you use the model, you can just give one new token and make one new context. You cannot do it all together, right? So you cannot give the whole sequence at once and you see all the context at once, right? So this was a kind of problem here, but up to 2017, we believed that this is the only way we can do it, right? Till the paper "Attention is All You Need" came out, and it somehow showed that, okay, you can just do self-attention, and you don't need to really do this, recursion anymore. By self-attention, you still can capture the time dependency, but this time you can do it more efficiently, so that you can process all the, tokens inside the sample in parallel, right? So this is the idea of what we call a transformer-based language model, and this is essentially what you do see right now, right? GPT is a transformer-based, and BERT is transformer-based. Whatever you use in your projects, they are usually transformer-based. So the transformer-based basically use self-attention to build the context, and then this is going to hugely help us in terms of parallel processing, because you essentially can look at the whole sequence and generate all the context all at once. Okay? So the next thing that we are going to talk about is the transformer-based language models. So this is the topic of the next session. But one last slide before you just leave here. Now that we do know how we can train it, let's say that we got one LSTM, and we trained it on lots of data so that we believe this is working right now. Now, how we can complete a sentence with that one? It's good that we just practice imagining how it works, right? So if you want to just generate, use this trained model now for inference, for generating a sequence, what you're going to do, you're going to start with the initial state, right? The initial state that you had. So the empty state. You're going to start with this one, and then you keep on sending every single token, right? Every time you ignore the probability, because the probability is not important for you right now, right? You just look at the context. But you need to go through all of it, right? To get the context up to point t in time, right? Once you have done it for the t different time slots till you get into the last context, then you start generation. Meaning that you just pass the last context with the last token, and then you're going to get the probability distribution for the next token, right? And then you're going to sample from that token. Then you put that token back to the input, the one which you have sampled, plus the next context, right? And then you're going to sample once again, right? And you keep on doing this till you want to stop, right? Typically, how you stop, you're going to put one specific token, which is end of the sentence. And when that happens, then the whole algorithm going to stop. So this is the way that you generate it now. So you need to pass everything you had into your LSTM to get the context at the time that you are right now. And then from then on, you can just, again, generate one token at a time, right? So this is the token generation by recurrent language models. That's it for